we are having our ASTM session today. We're going to be talking about raster data management in Oracle database, and we have me as the host, Denise as the co-host, and we have our special guest, Albert. I think a lot of us are already familiar with Albert, but do you want to go ahead and introduce yourself really quick?
Yeah, I've been doing a few of these sessions already. So I'm part of Oracle product development, except they don't let me touch the code. So I just explain how it works and I help people use it. So spatial things, graph things. And I've been doing that for quite a while. I'm based in France, not far from Nice.
Awesome. Thank you so much. And we've been having these ASTM sessions for some time. So if you missed any of the sessions, we've covered a lot of different things like GeoJSON, REST, Python for developers, geocoding, and some of the fundamentals of spatial in general for Oracle. So if you've missed any of those sessions, you can always go to Ask Tom Spatial using that bit.ly link. And I think you can go ahead and get started, Albert. Thank you so much for having this session.
Well, let's go. Let's start then. So today we are going to talk about something completely different. So far, I think pretty much all of the sessions, well, not necessarily all, I didn't follow them, but many of the sessions have been talking about what the GIS people call vector data, which is point line polygons, rivers, roads, cables, land parcel, building on land. Today we're going to talk about something different. It's rasters. And so what is raster? We first are going to talk about that. What is it? How do they compare with vector data? Then we look at how do we store, how do we model rasters in the Oracle database. Very important next step will be how do we actually import raster data? We know how to import vector data. There are tools like GDAL. Well, we're going to use similar tools for raster. Then we want to view data. And for viewing, Spatial Studio. That's the answer. What else? Why would you use anything else? We're going to use Spatial Studio for that. And finally, we talk about what you can do in terms of processing rasters. We know that for vectors, you can do things like computing the area of like a land parcel. How long is a cable? How many things are near that particular cable? These sort of things. Well, what can we do with rasters besides just looking at them? So we'll talk about that. Yeah, before we go there, we do write that we do have a formal document, which you see the URL at the bottom. I think it's going to be placed in the chat as well, about a geospatial data platform. So the architecture of building the actual of a data platform that you could be building on Oracle using Oracle tools and practices. So databases, autonomous databases, especially Apex, Studio, data integration platforms, and also publication platforms. And there's a document here that will explain what are the bits and pieces and how you can use them. So this is about essentially everything you really want to know about rasters, but we're afraid to ask. Here is a pointer to the documentation, and I encourage you to read this documentation. That's something I may not always say because some manuals are really, really not that useful. This one is really one of these really good manuals. It has a very strong section over the principles and how things work and why do we do certain things. So the principle, the process, the terminology. And then there's another section which has all the details, the signatures of the code, the PLC code packages. I really encourage you to read that, at least the first chapter that will tell you all about rasters. So let's look at what are rasters and how do they compare with vector data. Well, rasters and vector, one big difference is illustrated here. We do take track of time. Okay, sorry, 16:06. Is illustrated here. Vector data is precise. It will tell you that something is here through spatial coordinates. Like, for example, this point here is at that particular spatial location, so longitude, latitude, somewhere, someplace. Raster is representing the data as a grid of cells. Each cell has the same size, and each cell maps to an area on the globe. So there's a concept of spatial raster resolution we'll see right after. So depending on the size of these cells, well, this may or may be more or less precise. For example, here, all we can say that this particular point is at that cell. If that cell is like 1 square kilometer, then we don't really know where the point is, just there's something there. If it's 1 square meter, then it's a bit, it is more accurate, more precise, not accurate, precise. If it's 1 square centimeter, and it's probably matching what you mean by the point. Keeping in mind that the points, so the vector, the lines, and the areas are really abstractions. So nothing is a point. We tend to think of a customer locator being a point, but the customer is not a point, it's a human, first of all. And the location will be something that is coming from a geocoding process, which will deliver a point based on address. Where is that point? Depends. It could be on the street in front of the house of the place, so somewhere there. Could be at the entrance, could be on the roof. So we don't really know where it is. Raster now will actually, for this case, maybe highlight multiple cells to indicate the shape of the area covered by the house. So for a line, similarly here, that line has 3 points. A raster line will essentially light up all the pixels on the path of that line. So it will use much more space. This one is just having these coordinates. Here we need to store all of these vertex, all of these cells. Actually, we need to store the entire grid, even the ones which are empty. They still have some kind of content and some existence. And for an area, the same thing. We fill all of these things. So what's the big difference? Vector data is precise. Raster is approximate. We don't know where things are exactly. We can see they are there, but we don't know where they are. Vector is sparse. It only requires storage of the things you have. If you have just like this point area in line, that's what we need. Whereas for raster, we need to store the complete matrix. And depending on the resolution of the cells and depending on the size of the area, this could be a lot of data. So in other words, vector is not really consuming much space, even though you may have lots of them, they don't consume much space. Raster will consume much space. In fact, vector is more CPU intensive in terms of computation. Raster is more storage. So it's easy to go into terabytes, tens of terabytes of storage. Imagine a complete coverage of, the US, for example, at a high resolution with like 1 square meter per pixel. That's a lot of pixels, and that's a lot of storage space. Vector is good for describing map features. Like that's a building, that's a high voltage line, that's a river. Raster is more for representing large field structures. So in other words, things which are not necessarily precise. A good example is this separation between savanna and desert. At what point do we step from savanna to desert? You can't really draw a line there. No, there's nothing that says, well, this is savanna, this is desert. It's just that suddenly there are less and less grass, and at some point there are not much grass any longer. So we say, well, maybe no, I mean desert. In a raster, that's easy to represent because you will just have cells, and these cells will contain things like, the average vegetation per square meter, or the rainfall per square meter or per square kilometer in June. And depending on these values, you may decide, well, this is actually savanna, it's actually raster, it's actually desert, because that's your own definition. So it's continuously field structures. Raster are easy to draw because they essentially are a picture in a way. All you need is to make sure that each cell with its value becomes a pixel with a certain color. And so imagery is an example of raster, and typically requires much more storage space. So again, like I said, resolution is important here, coarse, fine resolution. Depending on what we talk about, I can show you some rasters where the resolution is really, really coarse. It would be like, I think maybe 10 square kilometer per pixel. On the other hand, imagery, like satellite imagery nowadays with the latest satellites, will go down maybe to the 30 square centimeters, so very, very small, or 1 meter, 1.5 meter, which is already good because you can really see lots of details. So depending on that, you will need more space. But in a database, how we actually abstract a raster, it is a grid. So we're going to abstract as a grid, and each cell contains a number. Like here in this example, we have 2, 5, 4, etc. This is really a color code. You could see 2 means green, no 5 means this light blue, 6 is red, so this is 6, 6, 6, like that. Black or gray here is 0, like that. So that's what we have essentially. So numbers. Now these numbers could be colors. They could also be the average rainfall in June at that particular area. So where do they come from? Well, they come. A lot of them will come from satellite imagery, so remote sensing, aerial photographs, orthophotos. Nowadays, they could come from a drone flying over some area, and for example, recording the placement of swimming pools for all sorts of purposes. And there's also gridded data, where the data is really numbers, so nothing visual, but more like pressure, temperature, and this sort of thing. Okay. Now, images, in particular, can be composed by one or more bands. For example, your typical imagery will be red, green, blue. There's a red channel, a red band, a green band, and a blue band. So red, green, blue. And by combining these, we can get all the colors, pretty much any color. So in that particular case, our raster will have multiple bands. Instead of having just one of these matrices with multiple bands. One will contain the intensity of red, green, and blue. And so this intensity typically will be between 0 and 255. That's also what you observe when you use like HTML colors. Like FF0000 would mean red. 00FF00 would mean green. Okay. So a raster can have multiple bands, 3 bands typically for imagery, maybe 4 bands. The 4th band could be something like infrared or some transparency channel. Hyperspectral images or multispectral will have tens of bands, maybe hundreds of bands if it's history. If we keep a raster which has the history of rainfall, square kilometer by square kilometer for like each month for the last 10 years, that's a lot of bands. And so all we need to know is which band means what, and then we can find out about that history of data. Now, one problem with raster is the size. And so here's an example of a raster that's formed by 3 bands, so probably red, green, blue, giving you this image. Now, let's say you want to show this image on a web page. Well, this may be 1 gigabyte, 1 gigabyte, 3 gigabytes. It's just not possible to fetch 3 gigabytes of data just to show it on a browser page, just too much data. So therefore, a very common concept in imagery is the one called pyramiding. Pyramiding is simply that you take our big raster. So this is our big raster here at the bottom. You see it here. And from there, we derive smaller and smaller rasters, forming a pyramid. This is conceptually easy to do because you can say, when here I have 4 rasters, four cells, how do I compute that one? Well, how about using the average? How about doing some sort of simple numeric computation between maybe this one, also maybe including the one that are nearby it, and same thing there. And so we end up gradually producing very small images. And then zooming in simply means, well, we're going to find out what is the current scale, which is matching how many pixels do I have in my screen versus how many pixels do I have in the raster, deriving that as a ratio, and then deciding at which level I will start reading. So from the top, we probably have a very small thing, which will be turned into a JPEG that is just a few kilobytes, and then be sent easily to the browser. And then when I zoom in, that means stepping down the pyramid until I go all the way here. I see there are some questions in the chat. Oh, no, that's just a discussion. All right, right. So pyramid, all imaging systems. The thing about pyramid is that it takes additional storage space. Like, for example, typically one third of the space, 40% of space. So here we have maybe 1 gigabyte. Well, the whole pyramid will probably have something like a third of this. So 300 megabytes for the pyramid. But the pyramid is essential because otherwise I would not really be able to view my raster. If I didn't have a pyramid, I would have to read the complete details here and send that to my client. That's not possible. Now, at some point, I'm going to zoom down, and we want to see a small piece of this. I'm narrowing to maybe one street or one building, and I want to see detail. How can I do that without having to read the whole gigabytes and gigabytes of stuff here? That's where imaging systems introduce blocking. So blocking is the concept of dividing this big raster into blocks. Each block has so many pixels by so many pixels. So it's very easy, like this, divide into blocks, so many pixels, so many pixels. So not like that, not like 4 by 4, more like 256 or 512 by 512, this sort of blocks. So something that is reasonably small, not too large to maintain a good ratio. And so when it comes to read, for example, that section here where my cursor is moving, it's trivial to say, to determine that I need to read this block and this block. Just look at the pixel coordinates here and then divide by the size of the block, the integer division of this, and then that gives me the indexes of the blocks I need to read. Pyramiding is easy. You probably want it. So there's an option, do I want it? That's easy. And you decide the way pyramiding is done. Blocking is a bit more complicated because at the end, you have to choose the block size. So we do provide some mechanism that allow you to automatically, we will pick up a block size that matches the data, but it is still within the constraints of what you want to achieve. Because you don't want to reblock every time. Cell depth. Well, now we talk about a grid containing numbers, but numbers that could be like 8-bit for red, green, blue channel, could also be negative numbers, could be much bigger numbers like floating point numbers. If I deal with like temperatures, well, they can have decimals, like it's 37.45 degrees Celsius, or it's so much of a pressure, so much of an indicator. So therefore, I can store all of these values using different types. From 1 bit would be for like black and white or mask, something I don't want you to see there, so something like that. 2-bit, 4-bit for classifying things, and then 8-bit unsigned, these are our color, so RGB, 8-bit signed for some signed value, then 16-bit signed and signed, 32-bit signed and signed, 32-bit real, and 64-bit real. So these will be for floating point numbers with decimals. This will be for integers. For example, if I want to model elevation, where the contents of a cell would be the elevation based on some maybe sea level, and I want to model the deepest holes in the ocean, in the sea, all the way to the tallest mountain, well, I need 32-bit for that, probably in meters. Now, 16-bit would not be enough. Maybe 16-bit sign would not be enough. Maybe it will, or 32 bits. Yeah? Compression, again, because of the sheer volume and size of imagery, it's maybe good to compress, make it so that it uses less disk space, so I can fetch it faster. Now, of course, the flip side of this is that I need to compress on the way in. That's okay, but I need to decompress all the time on the way out. So it's one of the decisions. Do I want to use less storage and compress, but then use more CPU when I read? Or am I okay with the size? I'm willing to have maybe much more space, but then consume less CPU in reading. We support two important compression. JPEG 2000. JPEG is a well-known compression method. It's the one used by your cameras. They produce JPEG images. JPEG 2000 is more modern. It compresses better, meaning that when you compress JPEG, when you compress imagery, you essentially lose information. Things may become fuzzy at certain places. So there is an acceptable level of loss that is here set to default quality 75 for JPEG. So this means that to human eye, you don't see a difference between compression and no compression. Maybe you would see it if the image was really blown up on a wall, large wall, and then you start saying, well, these pixels are a bit fuzzy. But other than that, it's okay for like the kind of usage we do, which is imagery on screens and maps. JPEG 2000 compresses better, meaning it will use less space and still maintain a good quality level of quality. Then for gridded data, so the measurements like the temperature, etc. But we don't want to lose information. We don't want something like imagine you have a spreadsheet, you zip it, you send it, someone unzips it, and suddenly numbers are different. That's not acceptable. So therefore, for these ones, we provide what we call deflate, which is really zip compression. And then finally, concept the concept of georeferencing. We call this GeoRaster because the rasters are located on the globe. So therefore, we provide a mechanism which makes it possible to correlate this thing here in the imagery, like in the photographic imagery or in the raster, with a feature on the ground. Like that restaurant here is in Long Lat here, and that means this particular cell in here. This makes it possible to have application where I'm seeing like a satellite image, and I overlay that with my road, my buildings, etc. I know where my buildings are in the countryside, exactly located. Where is this coming from? Well, different from vector data. Vector data is generally, much of it is publicly available. Now we have people who make it a specialty to collect vector data like roads and driving directions here and TomTom, but they actually crowdsource open data. OpenStreetMap is doing that. Many municipalities will provide vector data through an open data agreement, so it's free for you. Anybody can use that. Satellite imagery is different because it costs a lot of money to launch satellites, a constellation of satellites. If you want to have a complete coverage of the globe, well, then you need multiple satellites orbiting the globe and maybe at different places, so we can have a coverage that is like 24/7 of what's there. So there are actually quite a number of providers, space-going countries or space countries who have a space launching activities, who have capabilities like the US, well, the EU, Russia, and India also has these capabilities. Others will just make the launches achieved by commercial providers, but eventually there are a number of providers, and that's where you would buy the imagery from. And then there's Oracle. Now, Oracle actually has an open data repository. I'm going to click on this here, open data, oraclecloud.com. You may not know about that, but it's something that is really interesting to look at and that you should really look at, because there's all sorts of data here. Right? Explore repository. Well, there's this Bitcoin ATBG, Tomcat. I saw this Caltech pedestrian detection benchmark. That should look like useful. Autonomous driving data set, very useful. And then there's a category here called geospatial. And here I see a whole lot of, well, raster information, raster data on the globe. Now, it is not necessarily current data. It might be a few years old. Like, for example, here, this, I think this Landsat data here. So is from, no, this is very recent, 2021. Yeah. I think the other one here, Landsat, sorry, where is this? Oh, sorry, I need to click this again. This thematic mapper 4.5, that is dating from earlier. I think this is dating from 2014 or something, 2012. So you can go here, you have the links where you can download. But I said, these things are big. You see here, 25 terabytes for here. The other one was like 90 terabytes. So we need to really know what to do. But if you go there, you can then choose what area you want. So you could actually go there and get satellite imagery for your hometown, and then load in Oracle, and then start using it. Okay, so let's go back to. I see there's a question here. What about drones and raster data? Oh, Martin is asking about that. Yeah, I mean, drones are doing these sort of things. They capture imagery, just like satellites, except that they do it. They capture imagery wherever you go. There's one step, however, that is needed before you can use it, and that is, auto-rectifying everything. So putting everything so that they all match and they're all really sort of horizontal in the same plane, and same, that they're consistent with each other. For a drone, well, a drone will capture data left, right, and then fly over, etc., and recapture the same thing. So this needs to be cleared out, and so there are softwares for doing that. We have one of our customers in Norway called Nibio, who's doing this, is providing services for doing this on forestry. So images for drones are captured, then they are auto-rectified and normalized, and then they are turned into raster images, which can then be processed. What they use it is for detecting the state and health of trees, because Norway is a forestry intense country. So, okay, let's go back to what we were talking about here. Let's skip this. I had something. So, how are raster data structured? Oh, sorry, how are raster stored in Oracle? Well, we have a specific data model that is separating logical from physical structure. So, what does this mean? Well, no, rasters are very big. We can easily get terabytes of stuff when we store them in a database, and that's storing big things is complicated. So we need to find a way to optimally store this using the concept we talked about, so pyramiding and grids and also blocking. And so we decided to choose a model where we separate logical, so the red table, from the yellow table. The red table is where we have all the rasters described. Here it says raster 11, 12, 13, 14, 15. Why? Why do we have 11, 13? Well, because raster imagery, satellite imagery in particular, is generally, pretty much always, delivered in tiles. So you get a tile that may be, well, depending on resolution, maybe, I don't know, 50 square kilometers, 50 by 50 kilometer, or 10 by 10 kilometer, and another one 10 by 10, 10 by 10, like that. So everything has been cut up like that. That's not the way satellites capture data. That's how the provider, like for example, Airbus, that's what they do. They will receive the raw data, they will clean it out, auto-rectify, and eventually, at the end of the processing, store these things as really neat chunks of maybe 10 by 10 kilometer, really neatly arranged next to each other. Okay? And so that's what this is. So each raster here will probably correspond to one TIFF file or one JPEG 2000 file you get from your supplier. So one step would be to load all of these in the database, and we'll see how that works. But from a modeling perspective, so here we'll have what is called metadata. Each raster has metadata. Now there's metadata that is when it was captured, how much it cost, what time of day, who's the provider, what satellite, what kind of camera was used. But there's also physical metadata that says, well, how many pixels by how many pixels? What compression? How many levels of pyramid? What kind of pyramid? What kind of georeferencing parameter? What's the coordinate system of these things? So metadata. A footprint also, because each raster will occupy an area on the globe, typically a square or rectangle. So that square and rectangle will be stored in here. And then there's going to be a pointer to another table, which has all the blocks. Yeah. Remember, we cut up our things into blocks, and these are the ones which are going to be stored in here. All right. So you can have multiple of these RDTs. For example, considering this would be old data, it would be new data. So for kind of partitioning, you could also partition a table, or you could have this, multiple sharing table, or you could have this with pointers all over the place, which is probably not a good idea because it might be difficult to understand. All right, so structures are like that. Let's see how do we actually load these things in database. So the process for doing that seems complicated, but really it's not that complicated. With the steps, simply because all of these steps, most of them will be done by the tools you are using. So you don't really care about, I need to do this. So the first step will be, I need to create the raster table, the red table, then the yellow table. Then I need to initialize the raster. Initializing means simply telling this particular raster, it goes into that particular RDT. Then I need to load the bits into the pixels into my database. And there are two ways, what I call the push method, which is I'm running some tool and that will write to a database, and the pull method, where the database itself says, give me these things. So for like a CSV files, it would be like here using SQL loader, and this would be using a external table. And then there are stuff like setting up the georeferencing, setting the pyramid, and at the end, creating a spatial index of the footprints. But all of these steps here will typically be done as a single operation. You say load the raster and everything will happen. Even these two are optional, they could be done automatically, but it's probably a good idea, for a DVA at least, to really control where are the RDTs going. They are going to be really big, so which table space or which media will they be stored? In terms of tools, so we have tools available like a Java command, etc. Mostly what people are going to be using is going to be GDAL. GDAL is an open source framework that deals with all sorts of data, including raster and vector data. And so includes command line tools for loading and importing, exporting. And then there's a commercial tool called FME from Safe Software that's well known in industry that is more powerful. It has a nice GUI and it can do things here. It can automate processes. This is more about something, well, it's a library, it's APIs, it's command line. And if you want to automate the process, well, you have to write code for that. The code would be scripting. There's also database driven. This is the pull method. So we have a method, a PLC function called SDO translate that will read data from files and bring into a database. This is not possible in autonomous databases, simply because it uses external callouts. And these are not allowed in autonomous databases. But on-premise, you have a choice of using this or this. There's also what we call the GeoRaster ETL, which is really a GUI and a wrapping that uses GDAL and provides a sort of automation like FME would do. So you say, I want to load these files. These are my blocking parameters. And then this tool, this Java tool, we just go ahead and read one of the DOR in parallel and load everything. So make it easier for you. Otherwise, you do your own scripting. Python is very nice, or just shell scripts. So creating the raster tables is this, creating a table. And notice here we have all sorts of problems, maybe name of source file, description, the date of load, etc. And then there's an object type, data type called SDO GeoRaster. Just like we have SDO geometry, we have SDO GeoRaster. And inside here you see there is the footprint of the raster, the extent. The metadata is in XML because it varies in structure. And then these are the pointer to the blocks. So the name of the RDT and a unique ID in that RDT. You need to create the RDT themselves. These ones are a very specific structure, so we provide an object type for that, create table, blah, blah. If you don't create it, it will be created automatically. And here we have essentially a set of blocks. So each row in that table has the blocks of the binary content, the pixels, as a blob, the footprint of the block, and then this is the index of that block in the whole scheme of things. So what level of pyramid, what band, what row, and what column. So let's see how that works. Using GDAL, I'm going to try and do a bit of example here and then run that. First of all, GDAL, I think it stands for Geographical Data Abstraction Library. It's available at GDAL.org. It's open source. And so, right, okay, you could build it yourself if you want, if you're really brave. It's a bit of a, not so easy, let's say. And so therefore we choose to provide our own builds that include our own driver, because that's what GDAL is, GDAL Translate is using. The concept is I have like a common set of APIs, and then I have drivers or plugins, a bit like JDBC drivers. So we do our own builds that include the proper driver for GeoRaster and vector data as well. Initially, we used to include that with the database. So if you're running 19C, you will find Oracle Home, but it's an old version. It's 2.4.0. It's pretty old. It works, but it's not what you want. Where you want to add something more recent. And these ones, you can get them as patches. So you connect to your Metalink account, and you can download these as patches. So there's one. So we do builds for Linux, Oracle Linux 7, Oracle Linux 8, and then Windows 64. You download this and then you unzip and run this. Okay, setting it up, well, is just unzipping the archive, the zip file that you get, add to your path, do some setups, and then you get the command that you need, which is GDAL info will tell you about what does a raster file look like, how do things look like in the database, and then GDAL translate is the core of the loading process. There's also a picture of a book there. I think you should have the URL that in the chat. It's useful. I mean, the documentation is online anyway, but this is actually adding some examples and making it useful. So say here, just do this sort of setup. that's the place where you have installed it, setting up the bin, the library path, the bin path, the library path. Then these geodata, GeoRaster, and also are required, and same for Windows. And then you can start using it. GDAL formats will show you the formats available, including the one we want. And then the main utilities, GDAL translate, GDAL info. So let's see if we can do something here. So I'm going to go here. I'm in SQL plus here. Actually, I can just recall the command. It's easier like that. Set echo on. Oh, one important thing here is that raster is not enabled by default. If you try and use it, like you create a table with SDO GeoRaster, will tell you don't know that type. That's because you need to enable it specifically. And so like this. Okay, so, yeah, it was already enabled, so it didn't really do that. Then let's create the table. So at O2 here. Oops. Right, so here we see a two table, just like we saw on the slide. And now we are ready to load the raster. So loading the raster, I'm going to exit from here. Control D. There's a script here that does this. So load raster sh like this. And to understand what this thing does, well, let's look at this. Okay, get information. That's how you do it. So you say GeoRaster translate. Output format is GeoRaster. That tells the GDAL core to say to write to GeoRaster. The input file, and then the connection to a database with the name of the table, and then parameters. Remember, block size, well, 512 by 3. The coordinate system, if it cannot be recognized from the input file, then you have to provide it. And then this initializes the input file, the raster. So everything is done in one step. There are also parameters that say I want to create the pyramid at the same time. So let's look at how this works here. So it's 0.3, like that. And it doesn't work because I need to. Why is that not working? Because I'm doing that here on my Mac, and I don't have a build on the Mac that includes the Oracle plugins. So I'm going to do it here instead on the Mac. I'm going to do it in a VM which has everything, a Linux VM which has that. Like that. So you see it's loading. These things are very small. I think there are like 20 megabytes each. There are 4 tiles over San Francisco. Typically, raster will be bigger than that. It will be more like maybe hundreds of megabytes or maybe even a gigabyte. And so it will take a bit longer. But here, you see, it took about 5 seconds to do the whole thing for the first one, and 3 seconds, 3 seconds. So it's so right now in my database, I have everything up and running. So if I look at my database, SQL Plus, and I'm using a local database here. So SQL Plus got Tiger at local DB. If I was using an autonomous database, well, then the issue of the network is actually quite important, because if I have my, my terabytes of stuff running here locally, and I want to upload that into a cloud database, well, this is going to be over a network. So it might be better to actually transfer all this data on a file system in the Oracle Cloud, like in an OCI VM, and then from there, read and load. A bucket, yeah, but GDAL has no concept of that. It cannot read directly from buckets unless you use one of the file systems that make it possible to access bucket this way. Then you may actually need to copy it really on the file system. So here, let's look at this. Select star from US rasters. And here they are. So set, I'm using SQL Plus. I'm a bit old-fashioned here. But it's important, because if I'm using SQL CL won't show me anything. It doesn't know about objects. Maybe SQL developer might show me this one, but not the database actions. So I need to really use SQL Plus. And so here you see the metadata for one of these. We see the footprint, so the area covered on the ground. Then the metadata, it says that the bands are red, green, blue. It's undefined, means there's nothing, it's just numbers. It's 8-bit unsigned, a row, column, band. How many rows, how many columns, how many block, what's the block size? How many blocks do we have? The pyramid, so 6 levels. And then all of this magic here, that's the georeferencing thing. That's what makes it possible to correlate the raster with the real things on the globe. And then that's all there is here. All right. So it's all there. Now let me skip all this because otherwise we won't end up. I still want to touch a bit about database-driven import-export, even though we cannot use that for autonomous, but it is usable for in-house or on-premise, and that works by having you writing PL/SQL code that calls this method here in the PL/SQL package, which itself calls the GDAL libraries that are then loaded as an external process, and that is what is going to read the file and bring it. So the pull method, and that is done by using this sort of logic here. So you translate and then update raster like that. So this is really nice because you can then easily automate the process. I think we are running a little bit out of time. I don't know, a little bit late here. So how can I view my RAF? Because ultimately that's what I want. This is typically visual. Not only, but mostly it is visual. It is something that I want to see. So we do provide a tool we call the GeoRaster tool. It's a Java tool. It's in the database home. You see it here. So you run that, and it allows you to do things I've been doing. Like, for example, here you see creating the tables. There's also a tool here that says I can import. It also will start the GeoRaster ETL. All right, so it's a bit of a console over GeoRaster. But what we want to do is really use Studio. Right, so Spatial Studio is the flagship GUI tool, end-user friendly GUI tool for managing and dealing with spatial data, including rasters. So let's do that. Now let's see how I can use Studio to view what I just loaded. Let's go here and let's go and start Studio. Okay, Studio, yeah. Login as admin. Let's make this full screen. And yeah, right. So data, first of all, create data set. What kind? Is it like a spreadsheet? No, no, table view. It's actually from table view connection, and that connection will be Scott. That connects to my local database. I also have connections to autonomous databases and various others. Create. Okay, create Scott. Tables, views, GeoRasters. Okay, there's a special category for that. These are all for vector. This is for raster, GeoRaster. And I have US rasters, sorry. In PRS, that's another raster table. Data, I think it's vegetation indexes from an Indian state. So US rasters, yeah, okay. And now I have an option, two options, because there are essentially two ways of dealing with rasters from a database perspective. Okay? Here we talk about tiled, multiple rasters. We have 4 of them here, because that's the most common way GeoRaster data is actually offered. It is as rasters, as tiles. But I could also have a single raster in my table, maybe a single really big raster, maybe a multi-terabyte, no, really big raster. In that case, I would say which one. But here I'm going to do this. I'm going to say virtual mosaic. We'll talk more about that if we get a chance now. So choose the column. It's called GeoRaster. Okay. So this says we're going to read all of the rasters in my database, in my table, sorry, and then, well, merge them together and make them visible that way. So it's done. It was created. So let's do this here. Let's click and say, yeah, like here. Oops, no, click too much. Yeah, US rasters, it's here, so it's a table. If I look at the properties of this, it will tell me it's a GeoRaster. It tells me, yeah, what it is, GeoRaster ID, like that. All right, let's add this to a project. So let's create a new project. There it is. And I get welcomed by a world map. and I just drag it on the map, just like I would do for any kind of other data, like vector data. Okay, so here it is. So here it is. Now, meanwhile, we take a bit of effort for the background map to actually refresh, but here you see, here we have our auto photos or satellite imagery over, well, central San Francisco, the section of San Francisco. And I guess if you look closely, you see the streets, no, they map nicely. The streets are really going exactly. It's really nicely set up on the ground. There's one thing which is a bit annoying here, this black stuff around it. Why do we have this? Well, that's because of reprojection. That raster, or these 4 rasters we loaded, are using a local Californian projection. The map here is using the what used to be called the Google projection. Is the global Mercator or pseudo Mercator spherical projection that all maps are using. So we are using this Google, all of them are using that. And because that, well, the image had to be slightly warped and shifted. And that caused these black things to appear. So how can we remove this? Well, we can actually remove them. Although there are little issues with this, but we are fixing. So settings, configure, raster, bands, hide no data pixels, update. It's gone. Why no data? That's interesting in raster, because when we deal with relational data, we know the concept of a null. We have like a column of age, and that age is null. That means, well, we don't know the age. And so for raster, we have places where we don't know what's there. There's nothing there, essentially. But we have no way of expressing what nothing means. And so typically the way to do that is to use a special value. Like in the past, they used to do that for dates. You would use something like 1999, and that would be no such date, or 9999, and there's no such date. Well, that's the same thing here. So here for this particular raster, as we shifted, these empty pixels got filled with black. 0, 0, 0, no value, so black. And therefore here, we're just saying, well, don't show the black pixels. So it's not really nice because it has problems. If I zoom in really close, I will see things, well, hold on. There are some black pixels here that we should really be seeing. There are very few of these, however. So it still works nicely. But you can see there are some anomalies appearing when I look at this. Okay. So, and this is something we're going to fix. We're going to make sure that we don't see the anomaly, that we really handle properly all the data without losing information. That's it. That's essentially how we can load raster. Now I can also do something more, but I think we are running out of time slightly. Yeah, 10 minutes. So I want to talk about other things. But the things are, well, maybe I can do that very quickly. It's not going to take a long time. I'm going to just do this here, just to highlight another thing. So US underscore POIs and US streets. So I'm going to select these two, add them to my project, go back to the project, go back here, and now we have these two US POIs. Well, these are points of interest on San Francisco. Now, unfortunately, Spatial Studio decided to use this really pastel green that's not really easy to read. And for the streets, it uses this sort of really nice mauve, very nice colors, but it's not so easy to read. So now we can change this and change the color, make this like red and blue, clear and more visible. But then if we zoom in, we can see that these things align pretty much with the raster. So they follow the real streets, and they pretty much also follow the lines of the roads shown on the raster. So let's continue a bit of a couple of topics here. So I'm going to skip all of these screenshots here. You see, you can make things more visual using this approach. And move quickly into processing rasters. So what can we do with these rasters once they are besides looking at them? Now, looking at them is useful, but actually, can we do any processing where you can do something like derive more information? And so, yes, we can, through something called raster algebra, local raster algebra. So raster algebra is pretty easy to understand. You have all of these bands or rasters, they all must be compatible. So that a raster, sorry, a cell at a certain location of one raster represents an area on the globe, and that the corresponding cell in other rasters is the same area on the globe. So I can then start doing things like here, compute a new value by taking x plus 500, so one of the rasters, plus divided by another raster plus 100, and I'm getting a new output, a new layer. Now, why would I do that? Well, let's first look at the language that we are using. So this is really an extension of the PL/SQL language. So PL/SQL, why PL/SQL? Because I need to run through multiple rasters. Now here we just have one raster with just one band, that is just one call. But if I have a raster which has like 50 years of history of maybe a temperature recording month by month, that's a lot of them. And if I want to do something on all of them, like computing averages per year, or computing or comparing one, like the same month of each of the last 50 years, then I need to do some kind of looping. And so PL/SQL will do that for me. And GeoRaster provides the language. So the language is really expressions like this. These squiggly brackets here, squiggly 0, 1, 2, these are band numbers. Bands are numbered from 0. If I have multiple GeoRaster as input, then they'll be like this. So this is raster 0, band 1, etc. Compared with the raster 1, band 1 as well. So this, for example, will take for all of the pixels, the cells in my raster, the value of 0 plus band 1 plus band 3, and then divide by 3. So essentially taking the average. For a RGB raster, this will essentially turn my color raster into a black and white, into a gray cell kind of raster. Okay, same for conditions. So an example is this. I'm not going. Yeah, I want to show. I'm going to skip things here because we don't have too much time. Here's an example of one of these operations called find cells. Find cells will select cells, pixels, based on their content. So here I have a raster, and I want to select all the cells, all the pixels where band 0 is between 10 and 50, band 1 is between it, and band 3 is between these and values. Now, this could be, for example, selecting a certain color range of things, but it could also be selecting the rasters, which, for example, a terrain model with elevation, all the pixels which are above a certain level or below a certain level, or where maybe your wind speed is more than this, and pressure is less than that, and temperature is between this and that. And the way we do it here is that we read the input raster and the output raster in memory. Now, this does not read the pixels. So we're not going to read these gigabytes of stuff in memory. We just read the metadata, okay, the red table, not the whole thing. So we read both because we have initialized the second one to be an empty raster essentially. And so we apply find cells on GeoR1. We apply this expression that selects the cells and write them out with GeoR2. There are other parameters here. Like one will allow me to select the format of the output. Will it be also, for example, the same type or different type? Things like what values do I want for the unused, the one which did not get copied? So what are they set to? Well, by default 0, 0, etc. And once I'm done, I will write that back to this. So this here deals with the blocks, with the RDT. Take the blocks and then does some computation, generates new blocks. And it does it in parallel. So all of these functions are parallel enabled, which means I can now do this processing in a very efficient way on very large data sets. Of course, I need to have sufficient capacity in a database server to do that, like parallel 4, parallel 16, parallel 64, and so be able to very efficiently compute indicators or values based on rasters. You will get a copy of these slides, so you'll be able to read a bit more about that. So here are examples of how find cells work. There's also a raster update, where I update the values inside the raster based on algebraic expressions. There's the raster markup. This is the most powerful of this operation. It can take any number of rasters with any number of bands. We apply a number of operations, and each operation means we get a new raster with a new band resulting with that particular operation. An example of that one here is what I just said before, is the transforming of an RGB image into a grayscale image, a black and white photo. By doing this, so input raster GR1, output GR2, and then we apply that operation. Okay. Storage param null means we use the same storage as before, and the same parameters as before. Where is this useful? Well, here's one example where this is used. It's computing indicators like NDVI, the Normalized Difference Vegetation Index. There are a number of these indicators that are well defined and used universally. NDVI is an interesting one. It allows you to assess the presence and health of vegetation. It does so by computing the index by taking the near-infrared channel. So you must have input which has this infrared channel and the visible, so that's red. So infrared minus red divided by infrared plus red. Typically, that will be using data, for example, from a thematic mapper that has this sort of data. And the result will be a value between -10 to 10. -10 means there's nothing at all, no vegetation at all, so water, or maybe total barren desert. There's nothing there at all. 0 would be barren areas, like deserts or savannas in the summer. Shrub and grass, and then 1 means healthy for it. It's based on measuring the reflection of healthy vegetation compared to, well, maybe dying vegetation or just vegetation in the fall when it loses its leaves. Okay, and so here's how this would be done in Oracle. Raster markup, input raster, there's only one raster, output raster, operation, 3 minus 2, 3 minus 1. Why 3? Well, because that's the bands in thematic mapper, the one we saw before, where we could get this data from through Oracle. So TM band 4 minus TM band 3 divided by the sum of these two. So 3 minus 2, because in Oracle they start at zeros. That creates a new raster. But because we are producing numbers which have decimals, we must have a number formula that can do that. And so we use a 32-bit real. Another approach would be to maybe multiply that by 100 and round it to an integer, and then use integer. That may be using less space. And I think we are really approaching the end now. We are already 5 o'clock. I'm not going to go through the rest here, simply because we just run out of time. But there are some more, you will find some more operations which are more with pure image manipulation, like dodging, so adjusting the tone of an image to make it more balanced. For something like this, obtain this. So the darker area are lighter, the lighter ones are darker. And then this very important thing, mosaicing. Mosaicing is the ability to take multiple rasters and fuse them into a single raster, but in an intelligent way, considering that these rasters could be in different coordinate systems. They could be in maybe even different resolution. They may overlap each other. And so we offer a mechanism that lets you decide, well, when they overlap, what should we do? Is one taking precedence of the other? Like, is there one more recent? Is that the one that should be on top? Or should we actually merge everything and fuse everything together? So here's an example of this process. We see the input rasters, and you can see that they have not been taken at the same time, or maybe different time of years, etc. And that's not really looking very good. So by doing this merging based on statistics matching, we get something which is smooth and looks like a single raster. So I think that's what it is. Oh, and finally this. Remember, we said Studio is actually using a virtual mosaic. So virtual mosaic means I'm going to read all of this and merge them on the fly. The full mosaic means I'm reading everything and I'm writing everything out to a new raster. That might not be possible because just of the amount of data and the time it consumes. So here we do it on the fly, a virtual mosaic. And here you see the parameters that you can use to specify how should we actually merge when they overlap. Well, here they don't overlap anyway, so that question doesn't apply because they're all really neatly separated. With this, I think we can close. I see Ramu has posted all the URLs in the chat. So yeah, we do have a number of reference points as well. They will be on the slide that you get. You can follow these things. You have a pointer to the manuals. You have a pointer to a place from Oracle where you can actually get some of these, but again, be careful. Don't start downloading terabytes of stuff. Maybe your IT people may find that a bit objectionable. So go and select small areas and play with these. Yeah, I think we went through questions already. I didn't see too many questions going by.
Yep, I think we're good to go then. Thank you very much, everyone, for attending. We do have our next session on August 29th, and we'll be going over an introduction to spatial AI. So I hope to see you guys there. Have a great day, everyone. And thank you so much, Albert, for giving us this session.
Yeah.
Have a good day, everyone.
Thank you, everyone.